first we'll start off by reviewing things. I don't really actually need the projector. I'm just going to start off with a review of the factorial function. All right. Okay, so for those of you who, so hopefully you've watched a lot of the videos by now. I've broken them. Essentially, you can break them into three parts. Part one, which was the goal was to have that done by Monday. Part two, which is the more advanced recursion stuff, and then the third part, which was the recursive data structure, which bleeds into next week. And also, then there's two videos. Those were posted late Sunday evening, and then two videos have been posted on recursion specifically targeted toward your homework. So view them. They're videos that are there to help you with your homework if you get stuck, or to give you a good foundation to get going. I also pushed back the maze date based on the maze turn-in time based on the request of a bunch of students in the other lectures. So if you need more time on that, you have more time to do the maze. So, all right, let's get started with our first function with factorial. So to review, factorial, right? That was the first recursive method we learned. N factorial, we said, was equal to n times n minus 1 times n minus 2, dot, 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 all the way down to like 3 times 2 times 1, right? And the big realization that we made was that we could redefine n factorial as n times, and we could take this entire block and redefine it as n minus 1 factorial, right? That was the big key for there. And the way we can write, so the way we end up writing a recursive method is, well, the same way we kind of would write this a recursive mathematical definition, which is, well, let's go ahead and rewrite this over here. So for a recursive function to work, we need two things. We need the base case, which is the problem where it's become so simple that it's really easy to solve. So n factorial is 1 if n is 0 or n is 1, right? And then we have the recursive case, which is what if it looks like it's going to be a hard problem, right? Oh, we've been given 100 factorial. How do I solve that? And the answer is I would calculate, well, n. That's an easy part. I would do 100. And then I'd calculate what 99 factorial was. So n minus 1 factorial, right? So it's either 1 if n is 0 or 1, right? And we know, and 0 we just simply know from being told by math professors that 0 factorial is 1. And 1 factorial is obviously 1 because, you know, that makes sense. Now you can have as many base cases as you really want, but generally we just kind of keep the minimum number base cases to, you know, have less things to check. So we end up with this chain of calls where basically we go, to calculate 5 factorial, we do 5 times 4 factorial, which calculates 3 factorial, which calculates 2 factorial, which calculates 1 factorial, which returns 1, which returns 2, which returns 6, which returns 24, which returns 120, right? Passes that back up, and I went over that in the videos. So how do we do, now it's important also, the thing to remember is that the reason we have this base case is that it's the condition which tells us to stop. It lets the function know its work is done. Otherwise, if you don't have a base case, you've essentially created Mickey's broom, or in some cases of the legend, the golem. So, you know, where it just doesn't stop working, right? You've got essentially this program that won't stop until the stack overflows. So the base case is what tells the program we're done with our work, we can terminate. So to write this, we would do, and I'll just simply public static voids factorial, right? Fact int n. We would write it something like this: if n is 0 or n is 1, right? That's our base case. Just easy enough, return 1. we will just return we will return n times fact n minus 1. Just took me a second to remember what I was doing, what the thing I was working on was. Right? That's all factorial is. It's super simple and super elegant to do. All right. So now with that we can start with that we can kind of figure out what the Fibonacci sequence is. So the Fibonacci sequence, we'll break this into two parts. The first thing you want to do, and what I want you to at least turn in, is basically a recursive definition of a recursive program that calculates the 8th Fibonacci number or the 10th Fibonacci number using the recursive method. Once you're done with that, we can start exploring it, because the Fibonacci sequence is taught to me as the first recursive function, that I was exposed to, but it was a terrible example of recursion. It's actually an abominable program that we're about to write. Abhorrent, abominably abhorrent, as we'll see. So but it's easy enough to program, and it's super elegant when you do it recursively. So I'll start off with our base cases for the Fibonacci sequence. The first two numbers in the Fibonacci sequence are 1 and 1. The second number is 2. The next number is 3. The following number is 5. Anybody know what the next number is? 8. And what's the number after that? 13. Okay, so for the people who are not in the know, how do we know that it was 8 and 13? How does the Fibonacci sequence work?
It's the last two numbers added together.
It's the last. Yep. Each number is the sum of the previous two numbers. That's the Fibonacci sequence in a nutshell. So more formally, the nth Fibonacci number is equal to the nth minus 1 Fibonacci number plus the nth minus 2nd Fibonacci number, minus 2. So the next one is 21. The next one is 34, and so on and so forth. Right? We keep adding these numbers together. So essentially, we just keep adding each two numbers in the sequence together, and it actually gets pretty big pretty quickly. So let's see. So let's go ahead and write our mathematical recurrence relation for this. So I'll do it nice and big. Fib of n, the nth, where n in this case, the input is us asking, give me the nth Fibonacci number. So in other words, if I put in 3 for simplicity's sake, I'm going to return 2 back, right? Because that is 1, 2, 3, the third Fibonacci number. If I put in 5, I'm going to get 5 back because that's the 5th Fibonacci number. If I put in 6, I'll get 8 back because that is the 6th Fibonacci number, right? If you want to start from 0, you can, but it's fine. So the recurrence relation is as follows. Fib of n is equal to 1 if n is equal to 1 or n is equal to 2, right? Otherwise, we get fib of n is equal to fib of n minus 1 plus fib of n minus 2. So I'd like you to go ahead and start coding that up as a method in Java. Create a new class, create a method in it. That's the Fibonacci sequence static method. I suggest you return a long because it gets big otherwise. All right, and test it by test it out by calculating the, let's see, like the 8th or the 7th Fibonacci number. But once you've done that, the next thing is to explore what happens when you try calculating the 40th Fibonacci number. And if that works, by the way, try calculating the 50th. And if that still works, try calculating the 60th, and that won't work, I guarantee it. Not because the number's too big, though, but because your computer will eventually slow to a crawl when calculating this. And if you want to try to figure out what that is and why it's slowing to the crawl, you can try using system.current time millis, to time the amount of time that this will take, right? Get the start time of the calculation, the end time of the calculation, subtract them, which will give you which will let you know how long it took. So try that out, and then together we'll discuss what the big O runtime of the function we're writing is, and ways to get around this abhorrence.